Hello, everyone. This module is to explain cellular signal encryption. I want to recall uh, some of the key types we looked at in a couple of modules ago, public key, symmetric key, asymmetric keys, and then block cipher and stream cipher. And also, the situation here is that asymmetric key is almost impossible in streaming data. So we need to have a symmetric key. But the problem is that we cannot share the symmetric keys. So symmetric keys needs to be, and also symmetric keys cannot be one static keys. It should be dynamically updated. So I wanted to recall also Diffie-Hellman the key distribution. If you see this, then there is a known values. Okay, for example, here R and P, those two values are known from the initial. And then there is a random values. Values can be generated randomly at each site. And then there is some modular functions. And whatever the outcome of that modular will be shared with the other side. Okay, and then they can generate another modular. Then from that point, they will have the same key. So from this key, they need to generate the keys continually. How can we generate the keys? So generation of the keys for Wi-Fi is RC4 algorithm. But here we'll look at the algorithm so-called A5. Okay, right? This should be also A5. So at both sides we use A5, but up to this point we use A8 and A3 algorithms. If you see this internationally, mobile service identifications, right? This is temporary identifications. Depending upon that, anyway, they can share some values known and some values are randomly generated, and they can be shared. So randomly generated values, and then whatever they received from that modular, and then again the randomly generated values can be used, and eventually they can start with the same key, k prime. They should be the same. From this point, then we will apply A5, okay? A5. So randomly generated function, some of the keys that we already know, and then at both sides, they applied A3 and A5 algorithms, and then finally they generate the same key at the first key they can start with. And after this, A5 algorithms. For authentication, how can we do authentication? We have to first authenticate, right? Therefore, hey, we need to decide whether we continue to serve this guy or reject. Before we apply A5, let's say you have a mobile device here, some mobile station, okay? And you call, okay, in Europe, out of band, okay? Of course, that is not your home service areas. So you call MSC, which is in, for example, Switzerland, mobile switching, and then you look at home location register, but you are not there. Then it go further through all here in Westchester. In Westchester, it has also similar to this. So let's say if it is in Westchester now, then look at that. Oh, yeah, he is the right person. He is subscribing to our service. Please serve him. Then back to here, Switzerland. Now this is a Switzerland MSC. In the Switzerland MSC, put your ID here, digital location register. And then from there, this guy needs to serve you, right? This is more all can be done in your SIM card and MSC and foreign MSCs. Okay, so this is more straightforward. This that whole process is not yet onto your mobile device. Whole process is initiated from your device, but nothing replied back to your mobile device yet. This everything can be done, should be done backbone. Once it is done, then by using A5, we need to generate the key, right? So that's what we are going to do. As it says, it should be done in SIM card, A3 and A5 algorithm. And what is the A3 and A8 algorithms? These two will be done at the same card. And then this is a real encryption. Let's say you have a key, okay? And you have a frame number. Frame could be, there's some frame, therefore it is shared, right? You and your device and your carrier. But anyway, it is a well-known frame. But the content in the frames keep changing, right? And then therefore, ciphering sequence, which is a key, and there is a sequence of the message, M, but at time I, right? So these together will be applied to this exclusive OR operator, then it'll be a cipher, CI. This CI, they are the same. And then CI and then KI here together, exclusive OR operator, then you will have original message, MI. So over that wireless communication, what you can see here is only CI, right? You do not know what it is. That is what cell cryptography is solving right now. Okay, the algorithm there's a stream cipher implemented very efficiently on hardware. Design was never made public. Leaked to Ross Anderson and Bruce Schneider. I think there is some other guy's name, Nathan, but it's not completely, right? So general idea of a frame is that there is a 64 bits frame. It generates 228-bit sequence. Okay, the frame size is 64 bits, but it keeps generating how many? 224 bits of K finally, so that given 228 bits of a message, 228 bits of K key will be exclusive ORed to produce ciphers. Okay, that's what it is. The frame is a 64 bits frame. Frame and then the K together along through this A5, it generates 228 bit at a time. It keeps generating 228 bits. A key 228 bits message together exclusive OR, and then there is a output. Okay, keep doing this. So next to 228 bits of a message, for this message, you need to have another 228 bits of that. That goes together for that exclusive OR. Keep doing this. To do that, what is a frame? Frame is this. Lufsa. LFSR, 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 okay, LFSR, linear feedback shift register, linear feedback shift register, so that you may know that, oh, that is a linear, which is a lot simpler than polynomial or exponential feedback. Therefore, it keeps running by itself. And then shift, maybe it's a left shift, right shift, and things like that. So register is limited. What is the size of a register? Register, whole. We use a 3 LFSR. Whole 3L, the registry, the size of registry for whole this 3 linear feedback shift registers is 64 bits, right? So there is a 64 bits LFSR. Now, how many states available? Then 2 to the power 64 bits minus 1 states. So unlimitedly many states. 2 to the power 10 is 1000, right? If you multiply by 6, then there's a 60. Then 6. How many states? That is 10 to the power 18. 10 to the power 9, that is a billion, zillion, trillion, whatever, right? Okay. So what is LFSR? LFSR is a linear feedback shift register. Purpose is to produce a pseudo-random bit sequence. That is a key. So NFSR is not by itself does not produce key itself. So producing key is going to go through multiple steps. But this LFSR itself produces some sequence, bit sequence. Okay. So we set some bits for some special function that is done in this way. We use 3 feedback polynomials, okay? And then we set the clocking bit and tap the bit. This is very, very important. The length of this frame is 19 bits, 22 bits, and 23 bits. If we add them all, then that is 64 bits LFSR, okay? You could increase this, or you could decrease this very nicely, right? But basic idea is this. So you do not know, for example, oh, Verizon carrier uses how many bits of LFSR? Oh no, right? Not only that, what is the clocking bits out of that n bits? We need to set 3 clocking bits. Here's another non-deterministically known, right? We do not know. But idea is still remains the same. This is very efficient, very fast, can be done in real time. Tap the bits. This is another thing that we do not know. Which bits that we want to use for feedback, for shifting, okay? Feedback and shift can be determined by this tap bits. And then we do not know which registers will be used. That is determined by these clocking bits, right? A lot of non deterministic factors available in this algorithm. Therefore, this is strong, right? Um, Stronger than Wi-Fi. Why? Wi-Fi should be more general. Wherever you are, if you are eligible, then you need to talk to that Wi-Fi router. Cell phone, for example, is it the case? No. Yours is dependent on the carrier. If you're subscribing to Verizon, then Verizon is the only company can serve whatever this kind of things based upon the SIM card that is also owned by or given by that company, right? So your cell signals are dependent on the SIM card because the SIM card has this kind of information in it. Not only uh, like a mobile subscriber ID, right? So international IMSI or TMSI, whatever that is on the SIM card. All right. More specifically, therefore, if you are using these particular ones, for example, three LFSR, the size of each like this, based upon this polynomial. So based upon this polynomial means it tells you this by this two. Knowing these two means this polynomial. Okay, particularly this tapped bits. 13, 16, 17, 18 means that is the number of that bits, right? Same thing here. So we look at here blue bits, that is tapped bits, and then orange bit, that is a clock bit. Clock bit determines whether my LFSR is to be participating on this particular cycle of LFSR operation. Okay, and then this tapped bits, the blue bits, the number of blue bits are set already, right? So if this LFSR is used, presumably then these 3 or 4 bits will be used for computation. If this guy, second LFSR is used, then these 2 bits. If third LFSR is used, then those 4 bits are used to the exclusive OR operations. So you need to look at the operation. All 3 registers are initially zeroed. So initially we put all zeros there. This is the index right now, right? These are the index. But the value inside here is, there's a binary code. So ones or zeros. So initially all zero here, all here, all zeros. But these values keep shifting to this way. Okay, if this is used, then next one. So all shifted, bit by bit, shifting is needed. If this LFSR is used, then all of these bits shifted to left. If this is used, then all of these bits shifted to left. If this is not used, remain, no shift, okay? If you want to produce the output, then this will be the key. But for initialization, it's not really. You do not need this. That is for initialization. That's what we want to see. Okay. So 64 bits are used. In this case here, without stop and go clock, which means here clock bits are not clocking bits are not considered. So this initial cases, we go through all LFSRs. We looked at this, right? We do not use clocking bits. So we do not choose which LFSR is used or not, which means we use all three LFSR. And then this 100 cycles, this is 100 times. This is for loop in real implementation. In this case, we use the clocking bits so that at each cycle, we may have different LFRs are used. Sometimes all of those, sometimes only 2 of those. Okay, these clocking bits, if they are the same, okay, if they are the same, then they can be used, which means, I mean, majority. Since we have three LFSR for each different bits per different LFSR, let's say 2 of those set to 0 and 1 is set to 1, then the third one is completely different from the other 2, right? But the other 2 set to 0, so they are the same. So those 2 LFSRs are used. In another situation, let's say they are all set to 1. Then, because they are all the same, so all of those 3 LFSRs are participating. So at least 2 or 3 all LFSRs are participating in this computation, okay? And then we need to, after we do this, okay, then we need to generate. In this case, this 100 cycles, we do not use any outputs. It's discard. And after that 100 times, we use the output. So how many bits that we use for the cryptography? We have 228 bits of key is generated. For those 228 bits of key will be used to encrypt the size of message. What is the size of message? That should be also 228 bit messages. Okay, these 2 not to use clocking bit. These 2 are using clocking bit. But the first one we discard output. This guy we use it. Okay, that's what we are trying to do. So this is the initial states. All right. So we have tapped the bits. So first to LFSR. These bits, blue bits, are tapped. And we initially put all zeros, right? Put all zeros. Same thing here, all zeros. This is 0, this is 0, this is 0, this is 0. And this is the key that is given, okay? Maybe possibly from the carrier, signal carrier. Okay, so this key is in binary. Let's say if that is 1, 0, 1, 0, then that the first cycle we use 1. And then these clocking bits are to be considered. the first 2 cycles. Okay, it has 4 cycles. Remember that? The cycles. One cycle batch, two cycle batch, and third and fourth. How many iteration? These many iterations. So you should take quite a few time. So initially they are all zeros. Okay. So we take exclusive OR. So if we have 0, 0, then that is 0. 0 and 0, that is also 0 for exclusive OR. 0 and 0, that is 0. And finally here 0 and 1, and that is 1. So this is set to 1. We do the same thing here. Then these are all set to 1, right? Apparently. And we shift, right? And then next one is 0. So then definitely next one is also 0. So this goes up here. This is a 0. This is 1 here. This is a 0. This is a 1. This is a 0. And the next one considered. Then all zeros. Definitely there is a 0. Next one considered. Then this is 1. So this is 1, and this is 0, and this is 1. So this keep feeding into this, right? So at certain points, let's say this is a 0, and this is a 1, and this is 1. That may be the case, right? But even in this case, if it is initialization, we do not look at, we do not use. So without stop and go collecting bits, we keep doing this. Okay. Anyway, by having this 64 times and 22 times, then we have some numbers built in, right? That's what we do. That's what I want you to practice, right? And after that, after 4 times of the cycling batch jobs, and then we do generate key. Okay, we need to generate 228 keys. So assuming that, let's say we have this, okay. Yeah, by the way, here, before we do that, after we use all of these keys, okay, let's say the size of a key is 228, then we use all of this to this initialization. And then next one is for 100, same process, but there is no additional bits. In the second 100 times of that, we do not use this, which means, yeah, in this case, we do not use the key, the seed key, okay? So that's not, that key, like, we call that session keys, okay? Session keys. So each session, it'll be different keys is given. The session key is used to this. If session key is not necessarily the size of 224 bits, if it is shorter than that, then we should put some padding, all zeros at the end. So total size of the session key is 228 bits. So we have 228 bits using these session keys. Here 1010, whatever. In this case, 100 cycle, we do not use any session keys, but simply we do this 100 times of those things, not using this, but all of this. End up having that, we have this, okay? Then we can generate. So we have a register 1, 2, and 3. Okay. So initially this. So what we will do here is that we need to look at, now we need to look at this. Oh, by the way, here in this case, right, that 100 times, then we use this control bits the way that we would use here. Looking at these control bits, if any pairs or triples are the same, first and third ones, number 1, right? So we're not going to use this R2, but we're going to use R1 and R3. So we apply this exclusive OR operator among those tapped bits. Okay, so 1 exclusive OR 0 means 1, and 1 and 1 means 0, and 0 and 1 means 1, right? This one will be fed into here, and then all should be shifted, and this one should go out. This is output, so 1 will be here waiting for this additional exclusive OR. Whatever having this exclusive OR, then we will have, that is the key in this sequence. Okay, remember that by looking at these clocking bits, we will have at least 2 registers to participate. Therefore, this binary operator exclusive OR is still valid, still applicable, still doable, right? So this is one coming here and one feeding. And the next one here. So we have tapped bits. 1 and 0 means 1, and 1 and 1 means 0, and 0 and 0 means 0. So 0 will be here. So all shifted, therefore this will be out. 1 exclusive 1 means 0. So first key is 0. I don't know. This will continue to, right? I don't know how. So that's what it is. So I'm not sure why 1 coming here. It should be 0, right? And the next phase is that, so once we have that, then all shifted. So 0 will be here. And this will be shifted here. And therefore this, next time, these 3 will be considered. These 2 will be tapped. And this will be another tap because they're shifted. And this will be tapped, and these 2 will be tapped. This went out, right? In this way. And then clocking bits, this will be the clocking bit, this will be the clocking bit, this will be the clocking bits. F, they shifted. Then we'll look at these clocking bits. If they are the same, then next to the computation for the registers are these 2 registers, right? 1 and 1. Okay, they are the same. This is 0. So what we need to do is that we need to make 1 exclusive and 0 means that is 1, and that is fed into here. So 1 is newly fed, and then in this case, these 2, 1 and 0 and 1 means 1, and 1 and 0 means 1, and then here is 1. So 1 and 0 means 0, so 0 will be. So R3 at this point is updated 2 bits, R2 updated 1 bit, R1 updated 1 once in the previous cycle. Okay, so next one is this, right? And this, because these are shifted, and then this, and this, and then tap the keys, this. Oh, wait a minute, they are not shifted at this point, right? We use this and this together only. So they are only shifted. So clocking bits now 0, 0, and 1 here, right? So now these two guys will be considered. So this will continue, all right? And once you have these keys, okay, whatever the key is, then given this is a sequence of keys, right? So given messages, right? So once you have these keys generated from this A5 algorithm, and then this is a plain text, you cut first batch for 228 bits, and this is the keys generated. This is the size of the bits of keys generated from that algorithm. Then they do exclusive OR and then ship out. That is the algorithm. All right. I hope this works for you. All right. Thank you.